This is my physics from 211 lab 5. The purpose of this lab is to analyze the motion of a vertically stretched slinky when released from rest, determine why the bottom of the slinky remains temporarily stationary. The fundamental physics principles were Newton's second law and energy. The main result of the lab showed that the top of the slinky fell immediately while the bottom stayed nearly motionless. My coordinate system was positive x, positive y, positive z. And for my prediction, I predicted that when this slinky is released, the top will begin falling immediately while the bottom will remain momentarily stationary because a release of tension will travel downward as a wave. So once again, my main physics idea was Newton's second law of motion, which is equal to force is equal to mass times acceleration. My system was the slinky. My surroundings were everything around the slinky, and my initial conditions were at t equals to 0 were that the slinky begins fully stretched and motionless, with both the top and the bottom at rest, and all forces are balanced until the top is released. My main assumptions were that the slinky behaves like an ideal spring with uniform coils. I assume that air resistance is negligible. This slinky is released from rest with no initial velocity, and the collapse wave travels down the slinky at a constant speed. So this is for my first method. I use tracker, and here is the video. As you can see, the bottom of the slinky does not move, and any variations in this are likely from issues with tracker. And from my second part of my methods, I use GlowScript. These are the most significant parts of the code that were used to create a model of the slinky. And here is a video. So this is my model versus the observations. The one on the upper left is the GlowScript, and the one on the bottom right is tracker. So the similarities were that the bottom remained still at first for both of them. The top collapsed almost immediately. A downward moving collapse wave formed, and after collapsing, everything fell together. The differences were that the real slinky has dampening and friction, and therefore the model is ideal. The real slinky has collisions between the coils, while the model does not. The real slinky's collapse isn't perfectly uniform. The bottom in the real video likely moves slightly, which we can see here in the variations in the y-axis. Real slinkies have nonlinear spring behavior, and the model's collapse wave speed can differ from the real one. So my main sources of error were frame rate limitations, the camera not being angled perfectly vertically, difficulty marking the exact same coil and tracker, blur or overlapping coils, the calibration measurement uncertainty, like if I didn't know the exact length of the slinky. And real slinkies don't behave ideally due to coil friction, air resistance, or wobbling. So here are my two questions. What if the slinky were made of a much less stiffer material? If the spring constant or K was higher, the collapse wave would travel faster down the slinky, meaning the bottom would start moving sooner after release. The slinky would also stretch less under its own weight, so the delay before the bottom drops would be shorter. And what does that mean that the bottom of the slinky didn't move? While this shows that the changes in tension do not travel instantly, information about the release moves through the slinky at a finite speed. So it demonstrates how internal forces behave in real materials and explained why the bottom does not respond until the collapse wave reaches it. Thank you.